I thank you all for coming, but especially Clarice for being here and inviting me. Although I know absolutely nothing of biology and quantum biology. So this is for me, I feel like a student here, and I'm very embarrassed to be up here talking to you all because basically last night I had to go through all these, try to understand some of the words, the jargons that had been said yesterday, and remember that, yeah, once I knew something of biology, at least enough to get into university. So forgive me if I don't talk about quantum biology. I'll talk about the closest I could find in what I do, but I do hope that next time I'll talk about quantum biology. And so here we go, without further ado. So basically, oops, sorry. I'm still having fun here. So basically, I'm gonna, the closest I could get in what I do was using quantum states of light to do imaging potentially of biological systems. So, okay, this is where I'm going. Obviously, imaging, using quantum properties and quantum things to do imaging is pretty old, and I think the most well-known example is nuclear magnetic resonance imaging using spins. And this is also a reminder that not just women get forgotten in the Nobel Prize, but also, potentially racialized men. So this was a Nobel Prize in 2003, and to Latourbeau and Mansfield, and Demadian was not included in the Nobel Prize because essentially that they refused to admit that his work was essential for the nuclear magnetic resonance imaging. In fact, he was the one who devised the protocol to do the imaging. And still today, this is a not really controversy. It's recognized, but too late. So going from spins to photons, which is what I actually work with. So the idea is here to use the quantum properties of light to do imaging and spectroscopy. Of course, everything is quantum, so quantum biology, in a sense, biology. But I think what we mean by quantum biology is often just when we harness quantum properties specifically, right? So the properties of light that we mainly use in imaging are entanglement, interference, and photon statistics. There are infinite imaging techniques today being developed using either of these or all of these combined. And this is the system which is most used, but not the only one. Hopefully it's not going to be that. I mean, it's being superseded now by other technologies, but still, this is the main system, which is to produce photons that will be used in these imaging system. And it's called spontaneous parametric down conversion, where you have a nonlinear medium and you pump it with a laser, and basically you have a probability which is pretty low because it's a very inefficient system of producing photon pairs. And oops, sorry. And oh gosh, how do I go play again? I don't know. I'll just have to go back and play. So the idea is that, well, this was supposed to be a little animation, but yeah, so basically, so for each photon coming from the pump, we have a small, very small 10 to the minus 14 probability of producing a pair. And the system of the pair is that when there are always pairs. So at least when you see one of them, say in one detector, you know that there should be someone else in the other detector, another photon. And that's the basic principle. And when you check for them together, and we call that coincidence imaging or post-selection. This system, due to conservation of energy and conservation of momentum, has interesting properties, and we can actually tailor the spectral properties quite. These photons can have the same wavelength, completely different, very different wavelengths. Today we can tailor this pretty easily by A, using different lasers, and B, different crystals, and manufacturing the crystals exactly the way we want to have. If we want different spectral, temporal, and spatial properties. And basically, let me go forward. Now it's doing it. This animation was done by Daniel Tasca, which I found out giving a talk at his university, where he asked me where I'd gotten this animation from, and I said I'd stolen it from Gabo, and he said it's actually mine. But you know, whatever. And this system of photon generation actually is behind, has a lot to do with this year's Nobel Prize. The two guys on the left, Alain Spee and Clauser, didn't use this system of production photon pairs, but they used like the precursor of it. Anton Zeilinger has developed and used these sources greatly, and I think that's possibly one of the reasons he got the prize. But I think that in like 10 to 15 years, hopefully we'll have someone else in here with even more sophisticated photon source, because we cannot know when we're producing the photons. So we have a probability which is very low. We want an on-demand. I want a button that I can press, and that will give me a single photon. And this is being developed now, and we still don't have a good source for that. So hopefully that would be, you know, when we're old. And the fun thing about this is that also, I think Brazil is a pioneer in understanding and I'm certain, is a pioneer in developing the theory and the experiments behind the spatial correlations, which is what enables imaging with these photons. So these guys, Monking, Sebastião de Pádua, Paulo Henrique Souto Ribeiro, and then later Stephen Walborn. I mean, their work is essential not just in Brazil but in the whole world. These are the basic references, if you want, behind spatial correlations and spatial entanglement, which just means the following. Basically, they understood how we could tailor the correlations and understand the correlations produced at the output. So say I have a crystal here, and we have the laser coming here, and I'm producing photons. They're produced in these cones. Each cone is a wave, like a wavelength. So this is actually a continuum. But you always have two. So you'll have, for example, one's coming out to the left and the other's coming out to the right. So the sum of their energies has to be the energy of the pump. So they can have the same energy or different energies as long as the sum is that of the pump. But what we know is that they're always produced in opposite directions, and that gives me, and so if I find one here, I know I know that its twin is here, and if I find one here, I know its twin is here. So why is this cool? Not just because they're different. We can also do this in show not just that the position is anti-correlated, but also the momenta, right? So this is the basis of this kind of imaging, which is possibly the most well-known imaging with quantum states of light that exists today. It was actually developed initially by the Russians in the 70s, but not theory-wise, and then experiments around the 90s. And what has happened recently is that new camera technology has allowed us to make this imaging system much more practical and useful, because we didn't used to have camera technology that could actually sense single photons, and this is pretty recent. So what this allows us is to put a camera there and see single photons producing, wanted to obviously accumulate them, producing an image. So what this system is, so basically remember that you have the two guys. So imagine, so I have here, okay, I'm not going to get annoyed at it because I liked it so much. Okay, it doesn't like going there. Okay, this is that crystal and this is the pump. And so I have, you know, one of the photons here, the two photons, one at each side. Say I separate them, right? I can separate them by color. I can separate them by just spatially. And so one goes in this direction and the other one goes through a sample. And then the sample, then after going through the sample, it just goes through what we call a bucket detector, which is just basically a detector that just collects photons. It has no spatial properties at all. It just knows, you know, I've got 10,000 photons per second or whatever. So it just gives me a counting of all that light, okay, intensity, if you like. And then on the other side, I've got one of these fancy cameras, which is basically a CCD, which can be it's intensified electronically. But because it's intensified electronically, you have a lot of electronic noise. So what they can do here is, once you get a click on the right side, right, you trigger the camera for it to open its shutter only at that time. And so therefore you can basically cut out this excess noise because you have really short and very precise opening times. And you can do that because the photons are entangled and because they come, you know, together, the pairs, right? But the interesting thing about this is that you've got a sample here, and this detector, which is doesn't really see the sample in a sense that it doesn't have any spatial resolution. The one that sees the sample is actually detecting photons that didn't go through the sample at all. But to be fair, if I were to cut this, right, cut this connection here, actually I'm doing a correlation here. Whenever I get when I got it clicked, then I open the camera. Even if I had a very good camera, which today we do, and we actually, thanks to Josh Moore, we have one in our labs, that you don't have to trigger, you can leave it just open a full second and it will count single photons and will tell you where it will, right? Even if I do use that, if I cut this basically it's electronic correlation, I won't get an image. And you'll see why. I mean, basically I'm just sending this blue system through nothing, and then it has nothing to show me. So the first lesson about this is that entanglement doesn't allow you to transfer information from one place to the other instantaneously. But so this is kind of the downside, but what is actually happening is that we're looking into correlations. So basically, if this guy is blocked, then it won't trigger the opening. So in the places where this guy is blocked, it doesn't trigger the other place, so the other side. So basically, we're just looking at spatial correlations, and the image doesn't appear in either of these. Actually, it doesn't appear in the blue thingy. It appears in the correlations. And usually, whenever we're talking about entanglement, we're talking about that. We rarely talk about entanglement and only talk about measurements in one of the systems. Entanglement always involves a correlation, making a correlation between two systems. Sorry for the physicists if I'm saying, things you know very well. But anyway, the ghost imaging became this fad, and actually people are putting quite a lot of money into this today, companies. But we know since the 90s, it can be done classically. The difference is that Classically, you've got a caps on your visibility and contrast. But essentially the whole system, we have like a classical analog of it, but that doesn't make it less interesting. And this is what I want to point out. I mean, imaging with quantum states of light, it doesn't mean that we have to use quantum states of light to actually produce new technology. If the quantum state of light, if using the quantum state of light gives you the creativity to develop a system, right? And then this system, you find that you have a classical analog that's actually easier to work with, maybe, or cheaper. It's still, for me, quantum imaging, in the sense that we only developed that imaging because we went through the quantum route. And I think this is the main thing I have to say about this quantum biology, which I don't know anything about. But what I understand is sometimes you go through the complex route of thinking quantum mechanically, and then you realize that you don't need to think quantum mechanically. But the fact that you went through this route actually is positive, because you would never have had that question, or you'd never had that sort of development if you hadn't thought quantum mechanically. And so one of our favorite guys, who Einstein and Bohr, one of the things that they loved talking about was entanglement, and the other thing they loved talking about is quantum interference. And I love to put this image just because Bohr was a theoretician, but he realized that, in order to do an experiment, this is his picture, you need nuts and bolts. So please, all experimentalists, all theoreticians, don't forget we need nuts and bolts. So the principle of it is quantum interference, which is basically classic. It's just the same as classical interference, except the difference is basically that you're working on a single particle level, and that's just something that everyone knows by now. And I don't want to go through this again, but I often get the question, like, so is each photon, this is a double slit experiment, interference pattern, is each photon like making this whole thing? No, each photon is just a dot on the screen, but we can think of each photon as being described previously to detection as presenting that probability. So in a sense, it's everywhere. So basically these guys, I'm a big fan of Mandel, who died without a Nobel Prize, probably because he died too young from cancer. So whenever I don't know what to do, like physics wise, just go through his work and you'll find great ideas. Anyway, so one of the things is he basically combines, so he gets these twin photons, and he develops many interference experiments with these, one of which is this one, which is an interference experiment where he's separate. So again, this first part is just like imagine ghost imaging, right? You just separate one of the photons in that direction, the other one comes this direction, right? And then he gets another one of those crystals and does this again. And then, but basically what he does is connect the paths of one of the photons that come out of the first crystal, go through the second crystal too. This is not as easy as I'm talking, and I didn't want to like bore you explaining this really like long, but imagine this. I think of this as a double slit. So think that there's a possibility of the two photons being produced at NL2 here or NL1. So think of that double slit, and then whenever these paths combine, they create interference. But the interference here doesn't look like that fancy, nice this. Imagine each of what we're looking at is just one point, like one pixel. So if you look at one pixel, it's going to be on or off, depending if it's constructive interference or destructive interference. And it can be anything in between by just changing the lengths of these paths. Actually, that's the reason why sometimes we have on and off here, is because the two possibilities combine, coming from one slit or the other slit, they combine in a way that one path length is longer or shorter than the other, and that gives us destructive or constructive interference or anything in between. So here you have the same thing. So I can actually have two outputs of this interferometer, we call it, and one gives constructive and one destructive. And then if I block one of these paths, I get nothing. I lose the interference, which is, again, which is something that if you try to observe which slit this photon went through, you lose the interference. So it's the same idea. So that means that I get both, I don't have constructive or destructive, everyone just comes out the same. And so basically what we did was basically, I arrived in Vienna, and this is basically what we did, where we just used the stuff that we learned from Monking and Sébastien and Steve and Paulon, and say, well, let's get this 1991 experiment and use spatial entanglement, what we know today about spatial entanglement. So then we use a sample and we can get this image. So the difference from ghost imaging is that here I can just use this camera, which we now have because George Moll paid for it, which is great, thanks. But we had in Vienna because Anton Zeilinger paid for it. This camera basically just senses single photons without needing the triggering. So what we did then differently from what Mandel had done also was that we decided to use very, infrared light to probe the sample, and then the visible light, which was its partner, which doesn't have the same wavelength as it, right? Because twins don't have to be the same, to measure it. So basically this camera wouldn't be able to see infrared light, and the sample wouldn't be, it would be opaque to visible light, which was used for the imaging. So basically our idea was, oh, great, let's do that. Then maybe this was cool, but then we thought, oh, maybe the biologists will like that, because maybe they want to sample, so we patented it. And we're still trying to get the biologists to get interested in it. So any biologists, if they're interested in it, but we're working on it, and it has become a fad, and the whole world is working on it. There's so many groups working on this and developing it further. So in order for the biologists to be interested in this, or the chemists or whoever, we need good resolution. So we've been working on how to enhance resolution. What is the best way to get good resolution? For the moment, the same as ghost imaging, we're still stuck with resolution that's even a little bit worse than a simple optical system. So because our resolution is bound by our quantum correlations, which aren't as tight as we'd like them to be. So obviously, these guys use classical light for super resolution, which is something that really revolutionized imaging. We would like to try and harness they use different properties, like classical properties of light. We're trying to see if we can use similar properties of light and manipulations of light with our system to get super resolution, or to get at least better resolution. Because in the end, we discovered that mostly the biologists don't care so much about having a good camera at the wavelength, like mid-infrared or something. Depends. But they do care about having it well, with good resolution. If I can image something in the infrared, but it's a shitty image, they don't care. So we've been that's basically been a lot of our work after that, which is trying to develop. So this was work to develop, think of microscopy, and our friends in Berlin actually did we had like a theoretical development, and they did the experiment. And this is them looking at mouse heart with mid-infrared light. So we can do absorption and phase imaging. And then these guys developed a great idea, which was to actually do OCT, optical coherence tomography, which is a very, very useful system, which uses interference, classical interference, to obtain images, 3D images of samples. So you look at the penetration through, basically it's a very simple Michelson interferometer. So we can do the same thing, but with a different color light. And actually, this is one of the directions we've been really interested in, which is taking this optical coherence tomography version, quantum version optical coherence tomography, and seeing if we can actually get things get images that they can't. And one of the material science people became more interested than the biologists, and it's actually useful for ceramics and for looking into like cracks in wall. So this is basically what we've been, those guys have been interested in. And then just again, we can do this classically. Yeah. Which is great. I mean, I get all these papers because science is politics. So I get all the papers doing it quantumly, and I always ask, why don't you try the classical version? Because you get, I mean, the quantum mechanical one is just good because you've got less photons, but sometimes you don't need less photons. I don't care how many photons I'm shooting at the wall. I mean, it's not like I'm putting it through a live person's, retina, right? So sometimes what I want to say is like, sometimes the classical version is not developed further because it's the trend to have quantum in your title. And so basically we've got tons and tons of people developing the quantum stuff, and basically nobody taking forward the idea that if you do the classical version, you might actually get make it easier, cheaper, and more effective in some applications. So all of this you can read in our tutorial, which we made because all these groups kept writing emails to me asking how to align the interferometer, and I was fed up. So I said, let's write a tutorial. Actually, no, they invited us to do it, and I thought it was great. So this is aimed at students and postdocs. There's like theory. If you're a theorist, you can go and it's like, wow, quantization of the electromagnetic field until there. And experimentalists, we've got like all the tips and tricks, and then you don't need to write me an email, but you can if you like. I'm not against people writing me emails. And I'm just closing here. So basically, we've got recent developments of camera technology and photon sources, and this allows new imaging concepts. So I don't think this is in the end, that every day, every year, new imaging techniques come out, and due to better camera technology that give us ideas, even if we don't actually need them in the end, they give us the possibility to think beyond what we did, and new sources. So the quantum version of these experiments is great for delicate samples because you can image with very low light. But again, the classical can often be useful also. That's it. And then we've got this massive field going on, massive field with tons of money in Germany, United States, being invested into getting better. They just want to make things that we can take into a lab or just buy ready-made. So this is, if students working on this will definitely get cited. And yeah, and then the combination of new methods with old methods often is the great way out. So yeah, just thank these guys who put up with me, and you guys for putting up with me for more than half an hour, I believe. I don't know how long. Thanks.